I think it's on paper. I don't think they use the computer. It would be very,
Yeah.
very hard to do it on paper.
Yeah.
Yeah.
Yeah. If we do it on paper, it would be it would be super hard. Yeah.
Super hard.
Yeah.
All right. So here is the next problem. I don't know for sure, but I would assume that just because it's a lot like the other competitions. So we have a triangle ABC, and the circumcircle is gamma. And then we choose any point P on arc BAC. And we let Q be the intersection of AP and BC. Okay, so let's see. We'll try to draw a point like up here. And I'll call it Q. Oh, did they have some new, I think they changed GeoGebra. I don't remember seeing this. Maybe this animation thing has always been there. I don't know. Oh no, this should be Q. Sorry. So this is Q. This is P. The bisector of AQB intersects the circle at K and L. Okay, this is L. R and S are on the circle so that KA is equal to KR. And LA is equal to LS. That's R. And this is S. And PR and PS intersect BC at 2 points. And it looks like these circles concur on BC. Let me see. Is that? I'm going to leave these circles here just because I think it might be useful that I don't know why yet, but it looks like they concur on BC. So let's see. X and Y. Yeah, so I'm going to GeoGebra gets confused because I drew that line twice. So I'm gonna go hide this for a sec, and then I'm gonna draw this.
Is it through concurrencies on BC?
It's easy. It's easy to prove.
Yeah, if you name it as, can I name it?
And then I will unhide. Well, actually, let me do this. Yeah. So then.
If you let the circle with center K intersect B set, say E, then K equals to KP, which implies KL is perpendicular to AD.
One sec. So basically, are you saying it's easy to prove that these circles meet on BC?
Yeah.
Okay. So if I let it intersect at point B, then KD is equal to KA. Whoops, I accidentally hid. Let me draw this bisector. Sorry.
And we know that KL is perpendicular to AD.
Okay. Because yeah, K lies on angle bisector. So yeah, these KALD is a kite. So okay.
So LA equals to LD.
So LA is equal to LD. I agree with that. And then from there, how do we show that?
Well, this circle is defined as with radius.
So therefore we know D lies on the circle with center L passing through A and C. Interesting. All right, so I'm gonna unhide that circle. So we want to show KX and LY intersect on it.
This problem is really simple. It's easy to prove that K, DS are collinear. Likewise, LDR are collinear. Then we use Pascal and we are done.
Okay, so it's a simple problem. We just have to show KD and S are collinear.
It's just angle chasing because L is the midpoint of ALS, arc ALS, and we know that AK equals to KD, and KL is perpendicular to AD. So we know that AKL equals to LKD.
And LKD is half of AKD, which is, yeah, okay. So yeah, it's a simpler problem. So I'm gonna write it up quick.
At last we use converse of Pascal.
Yeah, the converse of Pascal. So since X, D, and Y are collinear, then KX and LY intersect on the circle. All right, I'm gonna type it up really quick just for the people on YouTube. So draw the circle with center K. Center K through A and R. Let it meet BC at D. Then we have KA is equal to KD, and so yeah, LA equals LD. So KA equals KD, and implies LA equals LD. And that means L is the circumcenter of ADC. So, and then from there, we want to show that KD and S are collinear, and that is an angle chase because basically we want to show angle AKD is angle AKS, but that's kind of obvious. So so angle AKS is half of arc AS, and angle AKD is yeah. So angle AKD is twice angle AKL, which is equal to arc AL, which is half of arc AS, which is angle AKS. And that means that AD and S are collinear. I'm sorry, KD and S are collinear. So are LD and R. So x, t, and y are collinear, implies that k, x, and ly concur on the circle by the converse of Pascal. So all right, so I will move on to the next one. It's a nice short little problem. That probably would have been hard for me like a year ago, but yeah, now it looks easier. Whoops, sorry. All right, so we have a triangle. H is the orthocenter. Let's check the chat. Yeah, this looks kind of short. XA is on the circumcircle of BHC. So that AH, so yeah, so we draw these three circles. And then we draw so yeah, we draw this circle. Is this the, no, that, I don't think that's the Humpty point, no. So let me, CH and BH. So this point, and this point. So this is X, this is XA. This is XB. This is XC. And we want to show that that is cyclic. H, XA, XB, XC. Okay. Just trying to move the question upwards. I want XA, XB, and XC to be more inside the triangle. Maybe like that. See, I'll shrink it a little bit. You think I should hide these circles? I don't even know what to hide, but. So we know the circumcircle of BHC is, they're all reflections of the circumcircle of AB, right? So all three of these circles have the same size as the circumcircle of ABC. I just reflected over each side. Maybe it's worth drawing. So I'm going to draw the center of this circle. Let's call it O. I wonder if O lies on the circle. I wouldn't be surprised. Whoops. Yeah, it looks like it does. So really we just need to show H, AB, H, XA, XB, and O are cyclic. And then by symmetry, the other would follow. So maybe we have just, is HO a diameter of that circle? It looks like it might be. Maybe this is an easy problem. Let's see. Yeah, we just need to show angle HXAO is 90. Yeah.
So can you draw HA and let it intersect again the circle with center A?
Can I draw what?
HA.
HA? Oh, the foot of the altitude from H?
No, yeah, HA. Line
Okay.
HA.
All right.
And intersected with center A. Circle with center A.
So like right here?
Yeah.
Okay. Sorry. So I think you meant like this, right? Was that what you were talking about, HA?
Yeah, okay. Just said the point, but HA is okay too.
Okay. But yeah, all I have to do is show HXAO is 90 degrees. That seems like it shouldn't be hard, right? I wonder, so the Humpty point, oh, you're trying to show those are collinear. Yeah.
Yeah. And draw the center of circumcircle of HBC.
HBC. Oh, the
Yeah.
center of it. Sorry, my bad.
Oh, it's the same as the reflection of O through BC, across BC.
Yeah, so O and E are reflections over BC.
Can you draw, I guess we are done. Can you draw AE?
AE?
Yeah.
Whoops.
You know that AEOD, the parallelogram.
AEOD is a parallelogram. Ah, good point.
Yeah.
So once we know that that's a parallelogram.
And we are done because AE is perpendicular to HXA from radical axis.
AE is perpendicular to HXA. And then
thus DO is perpendicular to HXA.
So DO is perpendicular to HXA and DXA is perpendicular to HXA. Okay, so really, all right, so I'm going to hide this. All right. I feel like we did a similar problem to this in the past. I don't think it was the exact same one, but it feels similar to something else. Okay, so let AH meet. Okay, so draw the circle with center A and radius AH. Through H. Let it meet AH at D. And then, so let E be the reflection of O over BC. Okay. So it's well known that, so OE, so AH is equal to OE. That's kind of well known. I'll say AH is twice the distance from O to BC, which is equal to OE. So, and then, so AH OE is a parallelogram, or AHEO is a parallelogram. And so AE is perpendicular to HXA. Or no, AE is perpendicular, yeah. And OD is so that means OD is perpendicular to HXA. And then, so since HXA is perpendicular to DXA, then we know those are collinear. So then angle HXAO equals and similarly angle HXCO equals 90, and so that means that HXA XB XCO is circular. All right. Good job on that one. Where did I go wrong? Angle, oh, I need a space here. All right, I feel like the picture makes it look harder than it was, which is, okay, this one looks maybe a little harder, I'm not sure though. So we have a triangle with circumcenter O, and D is the midpoint of OA. Okay. The circumcircle of BOC. So there's a lot of these problems with the circumcircle of BOC, right? They're often like some median or Humpty or Dumpty point things. But we draw the circumcircle of BOC. And it intersects AB and AC again. So we'll draw this ray. AB and AC at E and F. So here's E, here's F. Let me make E a little closer so that you can see it. There we go. OF and AB intersect at G. And OE and AC intersect at H. I like that they're making the points easy. Although I think I may have to hide something for, oh, nice. GH. The circumcircle of GDH intersects AB and AC again. So it intersects AB at M. Just being lazy, sorry. M and N. Prove that A. So we want to draw the intersection of MN with GH. And I wonder if G and H are midpoints of A, B, and BC. We'll see. and of AB with EF. I think they mean BC with EF. That doesn't, so yeah, I think this is the other point. And I'm wondering if those are just the midpoints. Maybe this problem's too easy again. It could be that's too easy again. Let's see. So we have, I forgot what these lines were right here. What was I trying to do with this line?
It is easy to prove that G and H are midpoint.
It's easy to prove that G and H are the midpoints. Why did I draw this line right here?
We just need to prove that OG and OH is perpendicular to AB and AC. So G and H is midpoint.
To view this to intersect OF with AB.
Intersect OF with AB?
Problem wanted to do. Problem stating.
Okay. So
it is just a homotopy.
Yeah.
okay.
Yeah.
You guys want me to move on to the next one?
Depend on you.
Okay.
Yeah, it's
Yeah.
easy.
So this one looks easy. Maybe you guys, I'll just draw it really quick. So we just have two circles. But basically we draw the common internal and then the common external tangents. Whoops. My mouse is very slippery. So I don't know if this is like a well-known property, but it's saying, and I think I might have done this once before. But it's saying we want to show that EG, FH, and AC are concurrent. Is that obvious? I think we did something like this a while back. I forgot. Is it obvious that EG, FH, and AC concur?
Yeah, we did a similar thing.
Yeah.
We used this as a lemma.
We use what lemma?
We used this as a lemma in a problem.
As a lemma in a problem. That's right. So yeah, this is this one. Let's see if there's a hard one. This looks harder. We could try this. Okay. So we have a right triangle. So we have a circle. Oh, this one's definitely, this one feels pretty hard. So it's like a curvilinear circle. So it's tangent to OB and OA and the circle. I forgot how to draw this using GeoGebra. Do you guys know? There is a way to do it. I just forgot. We want a circle tangent to AO, BO, and Oh, actually, since AOB is isosceles, it might be easier to figure out how to do that. So yeah, I want a circle tangent to AO, BO, and the circumcircle.
Well, its center
Okay,
was
so
on.
So I think it would just be this, right? So its center has to be on this, somewhere on this line, right?
yes, yes. Okay, so after that, you draw this okay, so you draw the midpoint of arc BC. Arc
Okay.
BC. Yeah. So let's call it E, the below one, yeah. So DE cut BC, cut BO at a point.
All right.
Okay. Yeah. So let's reflect it over OD, and the circle will be in tangent to OB, OA, and yeah.
So it would be F prime B.
Yeah.
Be the circle. Okay. So yeah, that might actually be helpful in the problem itself. So we have this. Oops.
You hide the other lines because the problem will be really complicated, I think.
Yeah, I agree. So is that good enough? Okay. So it's tangent. So this should be P. So it's tangent to OB at P. So this is R. This is Q. And this is S. We'll call this V, just because I don't want to use any of the other letters. Whoops. Sorry, I just don't like having a prime. Okay, so this is saying F prime. Whatever, I'm just gonna leave it like that for now. The line RS intersects the circles at X and Y. So this is X. Let me move it so that these don't look like they concur. T is the intersection point. Okay, so we draw the tangents at R and S to those circles RBQ and PCS. And they meet at point T. And then lines BR and CS intersect at W. Okay, so we're gonna need more room here. So BR and CS meet at W, and PX and QY intersect at Z. This is a lot of stuff. Wow. It looks like Z is on the circle. Oh no, not necessarily. So yeah, it's really that point all the way up there. Can we make it any easier to see? It's not that easy. Yeah. I think the only way to do it is just to shrink the diagram if we want to see the whole problem. So, sorry. I'll just let it overlap the problem a little bit. Let's see. So we have this point. T is where the tangents meet. And then this point right here. So T, W, and Z. And then let me hide a bunch of stuff. Too many lines here. So I don't think I needed that. Okay. I'm So yeah, I wonder if it feels a lot like disargs, kind of. I wouldn't be surprised if it was just like a single application of disargs. Okay. It's flying away. I'm not sure how important it is that we see point E. I don't think I want to delete it though. So if we wanted, I wonder if they pass through E. If that line, no, it doesn't. So actually okay, we need these circles for X and Y. So PX and QY, BR and CS, and then T. Do you guys want me to hide point E in these segments, or you think I should keep it there?
I think three of them lies on the radical axis of BRQ and SPC.
SPC. You think that they pass through, they lie on the radical axis of that?
Yeah.
I didn't think so, because like, if you draw that one, oh, it does look like it. Yeah.
And it's not hard to prove that.
Okay, so T lies on the radical axis, right? Because TR is tangent and TS is tangent. So do you think you've solved it?
T is on the radical axis because S equals to TR.
So how do we know that? So angle TRY is equal to angle
RPX. It equals to RES. It equals to YQS, and it equals to TSY.
YQS is TSY. Okay. So TRS is TRX.
T is on the radical axis of RPX and SYQ.
SYQ. So you want me to draw the radical axis of those two?
I think it's
RPX.
enough to prove that these two circles' radical axis is the same as the other two circles' radical axis.
Okay. So how do we know Z? How do we know Z has the same power with respect to those two?
That is because RIQB is cyclic, right?
Or what's cyclic?
We just need to prove it. XYPQ is cyclic.
Okay. Yeah, once we prove XYPQ is cyclic, Z lies on the radical axis. But
Yeah,
I guess that's just an angle chase.
Yeah. But the hardest one is to prove that TR and TS is equal to each other.
Okay.
And it is just angle chasing, and TS.
So that's also an angle chase because TRX is equal to RPY, so RBQ. So TRX is equal to TRY, which is RPY. And I think you could show that RPY is equal to XQS because I think that's angle chasing. So, okay, so now for W, so W has the same power with respect to these two circles. Okay. So basically, what?
Because RSCB is on the circle O.
Yeah.
Yeah.
So we just have to show the radical axis of these two circles is the same as the radical axis of these two, I think, right?
I think it's enough to prove that W is on the radical axis of two little circles.
Okay.
So just W.
Yeah, just W. Yeah.
You name the intersection of CS and the circle of SYQ.
This one, right?
Yeah. we need to prove that FT is parallel to BC.
FD?
Yeah, FD.
I don't think FD's, is it parallel? Maybe you're right. No, FD intersects BC. Angle YQB. So PXYQ is cyclic. Okay. Yeah, so that proves, so what Yash just wrote, the angle chase, that proves that Z is on the radical axis of these two, and then T we know is on the radical axis of these two, and W we know is on the radical axis of these two. Yeah, so we have to show that W lies on the radical axis of yeah, these two. So YQS then RPX.
I am confused. If that is true, then FD must be parallel to BC, isn't it?
Let's see. So, I mean, basically, we want to show is FRSD. Huh. No, we want to show B.
I'm sorry. Tangents are two little circles.
So we want to show that WR times WF is WS times WD, but it doesn't look true.
No, it's not true because tangents are to the little circles. They are tangent to little circles. So
okay.
now we have to prove that W is on the radical axis of little circles, but radical axes aren't the same, I guess.
They're not the same radical axis. So
Again, draw the WTZ line WTZ.
draw the line. Yeah, this line can't be the radical axis of the little circles because this point is on that little circle. Yeah. So there's no way that line is the radical axis of those.
So I thought that W, T, and Z is lie on the vertical axis of circle R, B, Y, and X, S, C.
Let me make 100% sure that's actually true.
Yeah. That is,
oh, it's not true. Well, oh no, it is true. It's the radical axis. Yeah.
Yeah. That is, we just need to prove X, Y, QB is cyclic. That is, we use angle chase, and we just need to prove TR is equal to TS.
Yeah, okay, we are done. We
Yeah,
were confused.
So how do we know W lies on the radical axis of those two circles?
Well, ZS times ZC equals to ZR times ZB. Sorry, it's not Z, it's W.
Okay, so yeah, so W lies on the radical axis of those two bigger circles, right? T also lies on the radical axis by the angle chase, but Z, to me, it just looks like Z lies on the radical axis of the smaller.
No, we just proved that ZY times ZQ equals to ZX times ZP.
But so that would mean it lies on the radical axis of these two smaller ones.
No, big circles is also because YQ is on big circle.
Oh, YQ is also on the big circle. That's what was confusing me. Okay. I spent all my time being confused over that one little thing. Yeah.
Yeah, it also confused me.
Yeah. Okay. All right. So, yeah, I guess Centroamerican isn't as hard, maybe. So angle TRS is TRX is RPX. And RPX, we want to show RPX as SQY. Is that obvious? Or TRS, I'm sorry, TRS is TRY, sorry, which is R. So this should be TRY, which is RPY. And let's see. Yeah, so SXPC. Well, SXPC is cyclic by definition, right? We just have to show BQYR. Those are cyclic by definition. That's how X and Y were defined. But PXYQ, it's just an no. But for PQXY, you did the angle chase, so I'm just gonna write it out. So PXYQ is cyclic. Let's see, YQB. Yeah. Gamma 1, gamma 2 are small circles. So yeah, gamma 1 and gamma 2 define the small circles, but then X and Y, X and Y are where it hits the small circles, and we need to show, oh, you're right. Yeah, my bad. So yeah, it's easy, but yeah, we want to show, we still want to show that those are cyclic. You're right. So angle SYQ is equal to angle SQC. Which is equal to angle S. So angle SQC, is it obvious that SQ and BR are parallel? How do we know SQ and BR are parallel? Oh, I think it's because SQ passes through E. So Okay, so basically, so angle YQB equals angle YSQ, which is equal to angle RSE. And we want to show RSE. So RSE is arc RE. We want to show arc RE is equal to arc BS, which is the same as saying arc BE is equal to arc RS. I feel like I'm going in circles now. Do you guys see why YSXPC is cyclic? I forgot why. It looks like an angle chase, but I don't see it all the way through. I guess we want to show BS and RE are perpendicular. So Yash, do you see the proof that those two are cyclic?
RXP equals to RPB equals to SCB.
Say that one more time. Arc.
RXP equals to, I cannot see the point.
Oh, sorry, my bad. RXP.
RXP, RPB,
Okay.
then SCB.
How do we know that RP is parallel to SC? So I think you said RPB is SCB, right?
Yeah, they're parallel.
How do we know they're parallel? Oh, I think that's probably just because we know R is the midpoint of arc AB. And we know E is the midpoint of arc BC. So RE. So I'll say R is the midpoint of arc AB.
We will use the perpendicularity here, I guess.
So I think we need to use
BAC is the right angles. We will use it here.
yeah. So R is the midpoint of arc AB. E is the midpoint of arc BC. And I think by an angle chase, since S is the midpoint of AC, that's enough to show that, yeah, hold on a second. So I'll just start out. So R is the midpoint of AB. S is the midpoint of AC. And E is the midpoint of BC. So then by an angle chase, arc RS is equal to arc CE. Yeah. Okay. So actually, it's easy. So arc RS is arc RA plus arc AS. Is equal to half of arc BAC. Which is equal to arc BE. So basically that implies that RE is parallel to SC. And SE is parallel to RB. So then once we have that, basically then we know that angle RBQ equals sorry. RXP is SCB. Yeah. So that means that our PQS is cyclic. I'm sorry, that means that PXSC is cyclic. And so is BRYQ. And then I'll just say, since we don't have too much time here, by an angle chase, angle TRS is equal to angle TSR. And so that means that T is on the radical axis of those two circles. So they give of RBQ and PCS. So and ZX. Okay, so by an angle chase, PXYQ is cyclic. Oh, we already did that angle chase. So ZX times EP equals ZY times ZQ means that Z is on the radical axis of those two circles. And then with W, whoops. WR times WB equals WS times WC. So that means that W is also on that radical axis. And that means that T, W, and Z are collinear. All right. So I think I'm going to stop here. So I just want to mention, so it looks like today we had like a big variance in the difficulties of the problems. So some were really hard, or one was really hard. Most of the others were not as hard. So if you guys have a contest that you guys think is good in the future that has, I don't know, like maybe more consistently hard problems, feel free to let me know either on Discord or in the comments. Let's see. So Sharigen. So I feel like Sharigen is usually easier than a lot of, like maybe on the easier side compared to the problems we've done recently. But yeah, it's getting harder to find difficult problems. So if you guys know of good contests, yeah, please let me know. But thanks everyone for participating. I know it's a big part of your day, but level 2 is hard enough. Okay, maybe I'll check it out. But we had some really nice solutions. So thanks everyone. If you'd like to participate in the sessions and you're watching on YouTube, feel free to email me at mgreenb801@gmail.com. The sessions are on Sundays at 10 a.m. So sorry, not 10 a.m. Now at 8 a.m. US Central Time. So thanks. Have a good one.